Here is the example. Integral of the square root of 4 minus 9x squared. Well, try doing it by substitution. It won't work. Try doing it by parts. It won't work either. Okay, so what we have to do is we have to try and do it in some other way. And here is the way that we're going to use. So, first of all, let's look at what form we have. Our integrand looks like something of the form a squared, the number squared, plus b squared, another number squared, times u squared, where u is, in general, for this kind of technique, some function of x. In this particular case, it's a particularly easy function of x, namely is x itself. In fact, in this situation, a is equal to 2, b is equal to 3, and u is equal to x itself. In other examples you're going to see later on, u may be something other than just x. But let's stick to the simple for now so that we can see how the method itself works. Alright, so this form is similar to something of the form square root of 1 minus sine squared. Now, it's not really the same thing, but the structure is the same. It's a difference of two pieces. One of them is just a constant, and the other one is a function. And remember, 1 minus sine squared of x is one side of one of the basic identities that I listed earlier. Okay? So what we have to do is we want to change that form that we have to something that looks like square root of 1 minus sine squared. Why? Because of course 1 minus sine squared is cosine squared, and so we're going to have to compute the square root of cosine squared, which is just cosine. So that's going to make our life a lot easier. Well, let's see if that can be done. So we're going to let x equal sine theta. In this way, we'll be able to change our form. Wait a minute, we're not going to be able to change our form into that one. We cannot change the square root of 4 minus 9x squared into 1 minus sine squared of theta by simply letting x equal sine theta, right? For one thing, under the integral, we don't have x squared, we have 9x squared. So instead of using x, we're going to have to use something different. Namely, we're going to have to figure out what the square root of 9 is. Well, it's simple enough, is 3, and put it in front of x. So we're going to have to change 3x to something else. But we don't want to change 3x to sine theta. Otherwise, our form, the integrand, will become 4 minus sine squared of theta. That's not the identity we have in mind, or it's not the form that we need for the identity. So what we need to do is we need to multiply the sine theta by something else so that the 4 that we have in there can be pulled out of the square root. Of course, the square root of 4 is 2, so we're going to multiply the sine of theta by 2. Okay? So this is a bit of a choice of numbers and adjustments that may take a little bit of a while to get used to, but again, after a while you should be able to understand its rationale. Let me go through that again. So let's erase the whole thing. So again, remember, we're trying to change 4 minus 9x squared into 1 minus sine squared of theta. So first of all, we want to change the x squared to a sine theta. Okay, so to sine squared of theta. So we would like somehow x to be equal to sine theta, but we have a 9x squared. So instead of just x, we need to change 3x to a sine theta. And then again, in order to get rid of the 4 which we have at the beginning, we want to multiply the sine theta by 2. Okay? So with this substitution, oh, by the way, before I go further, notice that this is a different kind of substitution than what we saw in the method of change of variables. Remember, in that method, we let u, the new variable, be equal to some function of the old variable x. Here, on the other hand, we're letting x, the old variable, be equal to some function of theta, which is the new variable. Okay? So this is why we call this an inverse trig substitution. So we're substituting in the reverse order than what we normally do. But once we've set up that correspondence, then we can say two things. Well, first of all, we know that 9x squared is going to be equal to 4 sine squared of theta. That's good. That's what we need under the square root, right? So if we change the 9x squared to a 4 sine squared theta, we'll be able to pull out the 4 and be left with the one side of the identity. But this also tells us that 3dx, if we compute the differential on both sides, that 3dx is going to be equal to 2 cosine theta d theta. And of course we need that because we're going to do we're going to apply the method of change of variable to an integral, so we need to change the differential as well. Alright, so with all this in mind, let's make the substitution. So we're starting from our integral. Okay. So the 4 remains a 4, the 9x squared becomes 4 sine squared of theta, and the dx becomes 2/3 of cosine theta d theta. Okay. So at this point we need to do a little bit of cleanup. So there is a 2/3, which is a coefficient that can come out of the integral, and then we can pull out the common factor of 4 from under the root. Once it comes out of the root, it becomes a 2. So altogether we have a 4/3 outside of the integral, and then times the square root of 1 minus sine squared theta times cosine theta, which is left over in the differential d theta. And this is where we're going to use our trig identity, because of course that square root of 1 minus sine squared of theta is the same thing as the square root of cosine squared theta. Running out of room, let's clean the page. Alright, so this is where we're at. So here is where the simplifying step comes in. The square root of cosine squared theta is just cosine theta multiplied by the other cosine theta that came from the differential. We end up with cosine squared of theta d theta. How do we integrate this one? Well, this is a trig integral. So from what we saw last time, either in the video or in class, you may remember that in order to integrate cosine squared theta, we need a power reducing formula, or if you want, the half angle formula, which will change cosine squared theta to 1 plus cosine of 2 theta over 2. Again, the 2 in the denominator is a coefficient. It can come out, simplify with the 4/3 and become 2/3 on the outside. That leaves us with a 1 whose antiderivative is theta, and a cosine of 2 theta whose antiderivative is sine of 2 theta over 2. And then of course now, since we've integrated, we have to add the plus c. And so as you can see, we have been able to integrate that function. So we can move on. Wait a minute, where are we going? We can't move on anywhere, because now our function, our solution, the function, the antiderivative we have found is in terms of theta. Our original integral was in terms of x. We need to go back to x. And this is probably one of the trickiest, not necessarily the trick and the most complicated, but the trickiest part of this method. How do we get back from the theta that we have used in order to integrate to the original x? Well, what we're going to do here is first of all make things a little bit easier by changing the sine of 2 theta into a 2 sine theta cosine theta divided by or multiplied by the 1/2 gives us simply sine theta cosine theta. Why is that? Well, we simply want to make things easier, and we make them easier by avoiding having to deal with the sine of 2 theta and splitting it down into the probably simpler sine theta and cosine theta. Okay, so now we're ready to try to do a little bit more substantial changes. So we need to get back to x. Now remember that our original substitution was 3x equal 2 sine theta. So that is an expression that in a way gives us sine theta. Well, remember sine theta, even though we use the definition of sine theta based on the unit circle, but can also be thought of as something coming from a right triangle. So let's draw a right triangle, and let's say that again we're going to use that particular formula there. So let's say that this angle is the angle theta. Now if you think of that formula, sine theta in that formula is equal to 3x divided by 2. I'm not going to write it down because you should be able to work this stuff out in your head by now. If you don't, pause and write it on your piece of paper. So if sine theta is 3x over 2, and on the other hand sine theta is in a right triangle opposite over hypotenuse, I can label that triangle as having 3x as the opposite and 2 as the hypotenuse. So opposite over hypotenuse, 3x over 2, it gives us the sine of theta. Okay? So once we have the two sides of the triangle, we can use the Pythagorean theorem to figure out that the last side of the triangle is going to be given by the square root of the hypotenuse squared, which is 4, minus the other side squared, which is 9x squared. Now notice that the length of the right side of the last side, this remaining side, is exactly the form that we focused on for our integral. That's good news. It means that we are structuring the thing correctly. Okay, so now let's try and find out what is our integral then. The 2/3 is just a constant. We're going to leave it there, not a problem. Okay, what about the theta? Well, if sine theta is 3x over 2, theta has got to be the what? Yes, the inverse sine of 3x over 2, right? So we're just going to reverse the sign. What about sine theta and cosine theta that we have to remain with? Okay, so what about sine theta? Well, sine theta is simply opposite over hypotenuse. In fact, we know sine theta from the beginning. It was 3x over 2, so we simply write that down. And what about the last piece, the cosine theta? Again, look at the right triangle. Cosine theta is adjacent over hypotenuse. So in our case, it's going to be the square root of 4 minus 9x squared all over 2. Now we have changed everything to C, to C, sure, I'm thinking already ahead to C. We've changed everything to X, and we have added our C, which we don't want to forget, and so that is our answer indeed. We have been able to integrate the function, switch it back to X, so that is our answer. Now there may be a need or a desire to do a little bit of cleanup with all those coefficients there. If you want to do that, by all means go ahead, but for all intents and purposes the integration is done.